My name is Michael Drass. I'm a PhD student at Technical University of Darmstadt, and today we are talking about the extension of a pseudo-elastic cavitation model for TSSA. It's really a little bit complicated. However, we did some testing on TSSA under cyclic loading, and there we found some really interesting and new insights of TSSA and the cyclic loading. So as a start, if we have a modern SSG facade, we need some point fixing. So TSSA is a good material. It's a transparent adhesive. It's really stiff. It has hyperelastic material properties. The viscose effects are not so important. But what is important in this case of a point fixing support in glass facade is that the aspect ratio between the width and the height of the joint is really small. So due to this, we get high stresses in the joint, and if it's stressed too high, we can get problems in terms of cavitation. Cavitation means the material is stressed in the axial direction, and then what we can see here in the materials, bubbles are growing, and this kind of effect is called cavitation. What happens to the material? Yeah, it's really easy. Due to the cavitation effect, we have some stress softening. So the connection behaves really ductile. How does it look in the experiment? Yeah, we did some testing on the TSSA under the constrained tensile test, or we can also say it's a pancake test because the joint is really flat. It's looking like a pancake. And due to this constrained tensile test, we have the effect of cavitation, what you can see here. It's a microscope image of the material, and it is stressed, and what you can see is the effect of the bubbles which are growing. Okay, but what is interesting, what happens if we have a cyclic loading on this? And this is what was never investigated, also not for TSSA, and yeah, I'm going to show you the cyclic behavior of the material and the modeling of it. So if we continue here, okay. We did some tests on the cyclic loading of a dog bone test. So this is really, let's say, we are familiar with this effect. So we have this cyclic loading of the TSSA. We have the virgin loading curve. If we unload the material, we have a stress softening. And if we have the reloading, we are at the same path of the unloading. So this is called the typical Mullins effect, which we should be quite familiar. So in this case, in the duck bone test, what we performed here with TSSA, we have the conventional Mullins effect. Interesting is what happens to TSSA if it's loaded cyclically in the pancake test. So first of all, I'm going to show you our experiments for the normal pancake test. So this is a flat bonded point fixing, which is just pulled in the axial direction. Yeah, the test specimen you can see on this slide. Yeah, this is TSSA. The thickness is 1 millimeter. We analyzed different diameters of TSSA, 1 times 40 millimeters, 1 times 50 millimeters. And if we plot the force displacement curves of our testing, we can see initially a very stiff material behavior. Then we have some kind of plastic niveau, let's say, and this is due to the cavitation effect. So if the stiffness decreases, the bubbles are growing, we have a softening. However, the material behaves very ductile. We can increase the load, and then we have final fracture at the end of the testing. So, but interesting is what happens if we do this kind of tests cyclically. And this is what you can see here, and this is really crazy. And there we have to go more in detail into the experiment. So initially, the first loading path, or the virgin loading path, it's pretty similar to these kind of tests. So the upper curve of this kind of experiment corresponds to these experiments because it's, yeah, let's say, it's the virgin loading path. What happens if we unload our pancake test? So we go to the first unloading. We have a reduction of stiffness. This is pretty similar to the Mullins effect. This is what we also know. And then what's really interesting is if we reload the pancake test the first time, we can see, let's say, recovering of our stiffness. And this is an effect what was never observed in a material. I'm not familiar with this effect. And we pronounce, or we say, okay, if we have this reloading, we have not the same stiffness as for the unloading. We have a healing effect. And this is what we can see in this crazy experimental testing curves. Yeah, we performed, I think, 7 tests. And what you can see here, the curves are pretty similar. So it's not an effect due to our, let's say, a false experimental design. We have a repetition of our curves. So the effect is really, really pronounced. And now we have to think how we can model this kind of healing effect. So to, let's say, what kind of effects, in summary, do we see? At the virgin loading path, we have a high initial stiffness. Then the softening starts. So the cavitation is growing. The bubbles are growing. If we unload it, we have the typical Mullins effect. We have a stiffness reduction. And if we have a reloading, then we have healing effect. So this is really crazy. And we try to put this into one model. I'm not going into the detail of the implementation. However, we tried to put it into a code. Okay, and yeah, this is then, let's say, the pseudo-elastic cavitation model. Yeah, as we know, we have a hyperelastic material, and hyperelastic material are always described by so-called strain energy density functions. There exist in literature many examples, and what you have to remember is we now take this pseudo-elastic formulation to calculate the softening due to cavitation. Then we extend it to the cycling behavior, the Mullins effect, and additionally we show or add some variables to have also healing effects. So this is what you remember, and the model is just able to analyze, let's say, the void growth in the material due to the cavitation effect. So this is what you have to remember. We're not going into detail here. So since this is a material model and it's implemented in ANSYS, we have to check and validate the model with experimental results. And this is what you can see here. We had in gray, you can see the stress strain behavior of our TSSA in the dog bone test. This is displayed in gray. So the experimental curves are always displayed in gray. And in black, you can see the numerical simulation of it. And what happens if we model such a dog bone test? Okay, there should be no void growth. However, the inherent voids are just deforming elliptically. Yeah, and as you can see on this slide, we can approximate the experimentally observed behavior of TSSA very well. But it's quite easy. This is what every model should do. Yeah, we also performed the so-called bulge test. It's a kind of inflation test of TSSA. So it's like loaded like a balloon. We blow up a balloon. And there you have a biaxial deformation in the material. It's a really tricky test. However, we learn a lot of stuff on TSSA with this kind of test. And in this model, we try to simulate the experimental behavior with the new pseudo-elastic model. And what you can see here, the experimental curve is also displayed in gray. And in black, you can see the simulation results. And they approximate the behavior of TSSA quite well. Okay, so let's say this is more standard. Easy material models and hyperelasticity should cover this. What's now new is we want to model also the pancake test. And this is what happens here. We modeled here the pancake test with a diameter of 20 millimeters, I think. And what does happen in this kind of test, we have this void growth and the softening. And normally, if you use commercial finite element calculation programs, you are not able to reproduce this kind of softening in this behavior. And with the new pseudo-elastic formulation, we are now able to cover, or let's say, to model the softening due to the void growth. So this is the new stuff of the model. And so, yeah, as a summary, we can say we are now able to calculate the softening due to the cavitation. And now we're going to extend this kind of model to the cyclic behavior. And the cyclic behavior, we experimentally analyzed the dog bone test. So we have the classical Mullins effect, softening, and then we extended additionally to the volumetric behavior, what we saw in our experiments. Okay. Okay, so as I said, the pseudo-elastic cavitation model is now extended to the cyclic behavior. And normally, if you have the cyclic behavior, we have the virgin loading path, and on the unloading path, we have a kind of softening. So this is here governed in terms of so-called damage variables. They are just increasing, or let's say if we have the virgin loading, the damage variable is 0. If we have an unloading, the damage variable is decreasing, so we have a decreasing stiffness. This is what you have to remember. And let's say classically, such kind of damage variable is formulated like this. And we did some parameter studies, and as you can see here, we have two parameters, R and M. And if we change these parameters, we can adjust the behavior on the unloading path and the reloading path. Okay. So this is the first extension of the model for the isochoric, so-called volume constant behavior under cyclic loading. And now we have to extend it additionally for the cavitation effect, because in the kind of pancake test, we have a volumetric deformation of the material, and due to this volumetric deformation, we saw that we have a kind of Mullins effect, which is governed by the volumetric behavior, and a healing effect. And so also here we extended the model with some damage variables and healing variables now. And we also did here some parameter studies. I think it's not working. Ah, no. Okay. We have here some parameter studies, and if we change our parameters, and we are not going into the details of the parameters, if we change the parameters, we can adjust the softening due to the cavitation effect. We can adjust our volumetric degradation due to the Mullins effect, and we can additionally add some healing, which is really new and what we saw in our experiments. Yeah, try to go next. Yeah. Here we can see the parameter studies of our healing effect, and yeah, as I said, we are not going into the detail of to understand the maths behind. However, what we have to remember is we have some kind of damage variables to govern the Mullins effect, so a softening effect, and we have kind of healing variables which gives us or recover our stiffness. Okay, and now we take the model and say, okay, on the left-hand side, we had this kind of weird experimental behavior with the cavitation effect, with the volumetric Mullins effect, and with the healing effect. And here we performed some numerical calculations in a one-element test, let's say. And what we can see here, the curves look pretty similar, let's say. But it's just a one-element test. We just wanted to show, is it possible to, let's say, is it possible with a numerical model to show such an effect? And with our formulation, we are now able to have cavitation, Mullins, and healing. Okay. But we also want to show that this kind of model is also able to calculate the real behavior in the pancake test, in the poker chip test. And this is what's going to be presented on the next slide. Yeah. Okay. So what we can see here, and we have to go very, very slowly through this slide, we start to use our model and calculate the complete dog bone tests. This is what you can see here. In gray, we always see our experimental test results, and in blue, you can see the numerical simulations. And with the parameters we found, we can approximate the isochoric Mullins effect very well, let's say. Okay, so now we have just added some variables, some damage or Mullins variables for the isochoric behavior. If you use this model and try to calculate the pancake test, Then we go on this slide, and as you can see here, we can cover the Mullins, let's say the softening due to cavitation in the virgin loading. And if we do some cyclic loading and only have, let's say, only the Mullins variables which are working on the isochoric part of our strain energy density function, we have a little bit of softening, but these kind of, let's say, these kind of results do not really correlate or approximate our experiments very well. So now we go onto this kind of model. We added now the volumetric Mullins variables on our potential. And what we can see here, we are now able to govern this volumetric softening due to the Mullins effect. So this is quite well. And in the last step, we should show also, is it possible to add our healing variables and recover our stiffness in the reloading path? It's a little bit of weird, and we try to do this. However, what you can see here on the reloading path, and this is the curves between each other. On the reloading path, you can see there's a little bit of healing. However, we had some numerical issues with the convergency because the material model is really, really complex, and let's say the numerical solver fails there. However, we were able to show that in general, the model is able to cover such an effect. The softening effect due to the cavitation, the isochoric Mullins effect, the volumetric Mullins effect, and the volumetric healing. Okay. I think, yeah. So in conclusions, we showed that we have a phenomenological cavitation model, which is able to govern the cavitation effect on the virgin loading. We improved this new material model by adding some damage variables for the isochoric Mullins effect, for the volumetric Mullins effect, and the volumetric healing effect. It's a quite really a complex model, and I think in normal facade designs we wouldn't use it. However, we just wanted to show as a university we are able to also approximate the experimental behavior of TSSA with a phenomenological model. Yeah, and yeah, as we showed, the model is quite okay. Let's say, however, if we look at the healing variables, it's not good for the convergency, and maybe there's a little bit of new research which should be done to improve this kind of model. Okay, so I think I'm at the end of my presentation, so thank you for your attention, and I'm open for questions.
Okay, thank you very much, Mr. Drass. Are there any questions from the audience?
I'm sorry, I don't understand very well, because you're talking about Mullin effect, you're talking about cavitation. These are classical problems in nonlinear elasticity since the 60s.
Yep.
In particular, the fact that you have a loading path that it is not coinciding with a loading path due to the fact that it is well known that no elastic energy, non-elastic strain energy, nonlinear elasticity can be convex. So all of them are non-convex. And you can have all kinds of sorts of behavior. Also cavitation. Sir John Ball from Oxford, he published in 78, I guess, a famous paper on polyconvexity of strain energy for nonlinear elastic material. And after a few years, he published a milestone paper on cavitation. You can have cavitation in rubber and with no damage, actually, because you just open a bubble and then you unload and the bubble disappears. And so I don't really understand why using this derivation of this kind of, you call it phenomenological model instead of classical models in nonlinear elasticity. Of course, you cannot find it in Abacus, but there are a huge literature on nonlinear elasticity.
Yeah, but let's say I know all literature on cavitation, and let's say it's really interesting that the people who worked on cavitation have not performed the experiments. So they assume they assume that cavitation effect, let's say, starts in a perfect material, so we have no inherent voids, and this is the first assumption, which is totally wrong. We prove that if we have an increasing porosity in our material, the cavitation load is decreasing, which is straightforward, let's say. However, all models in literature, there are some models or numerical model from the MIT, let's say. This is able to solve the cavitation effect numerically. However, I used this model to approximate my experimental data, just the virgin loading, and was not able to recover. Not the initial stiffness, not the cavitation point, not the post-fracture behavior. So in my opinion, the assumptions of John Ball and Oscar Lopez Palmies and so on, they started from a mathematical, and John Ball is a mathematician, I think. So they started to think what happens or what might happen to a material. However, we should also look at the experiments. And let's say the correlation between the cavitation, the volumetric growth of a bubble, and the cyclic loading effect and how it correlates to the Mullins effect, this was never done. So the cyclic pancake test, what we have seen here, this kind of experiment I have never seen, not in the literature. And I've never seen such a dominant healing effect in a material, in a rubber-like material. There are some studies, I think also from Italy, Palmieri, I think. He studied also some kind of Mullins effect for a dog bone test. And he said, okay, we have the Mullins effect, we have a softening, and he saw in his experiments that we have a slight healing effect. But I think if we do some experiments, you always have some deviation in our material itself. So there's a standard deviation in the curves, and the healing effect was not so pronounced. We can see here in our pancake test that the healing effect, for example, is really, really pronounced. We are talking about kilonewtons and not newtons. So yeah, this is what the model just looked phenomenologically. It's not, let's say, okay, if we look at the polyconvexity of this model, yeah, it's a damaged model, so we must not ensure the polyconvexity, not anymore, because we are not working purely highly elastic, not purely in the elasticity range. So, in my opinion, if we try to model the cavitation effect, we are allowed to say fail the criterion of polyconvexity.
Okay, thank you. Any more questions? No? Okay. Thank you very much, and Mr. Drass, once again.
Thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!